In the last online class, we started Unit 3, and in Unit 3, it was about spherical trigonometry, and I gave an introduction about great circles. So, great circles are nothing but circles which pass through center of a sphere, and small circles are those which do not pass through the center of the sphere. Okay, so if you have an understanding of that only, you'll be able to understand this definition. Now, this definition is about spherical triangles. We have already heard about triangles on flat surfaces. Okay, and the sides will be in centimeters or meters. Okay, now we are going to see about spherical triangles, that is triangles on surface of a sphere. Okay, so let ABC be any three points on the surface of a sphere. This A, B and C be any three points on the surface of a sphere, and I'm joining AB, BC and AC by arcs of great circles passing through them, which means that these 3 points A, B and C are joined not by straight lines but by arcs, and these arcs, you can see, they are part of a great circle. See, this arc AC is a part of this great circle which passes through the center of the sphere. Similarly, this arc BC, this is also an arc of a great circle which passes through the center, and similarly this arc AB is a part of this great circle which passes through the center of the sphere. Okay, so basically it is like when three great circles intersect, you are getting this required triangle. Okay, so this is known as spherical triangle ABC. Just as I said earlier, in flat triangles or in triangles in flat surfaces, the measurement of the sides will be in centimeter or meter, whatever the unit is. But in spherical triangle, it's not going to be in units of length. Okay, so how we are going to measure the sides, I'll show you how to measure the sides of a spherical triangle. Here our triangle is ABC. Okay, see, you have the center of the sphere to be some O, and in order to find the length of this arc AC, you have to join this point A with the center O. Similarly, join this point C with the center O. Okay, and if you just find the angle which is subtended by these two line segments, I am taking this to be some alpha. So this angle subtended will give us the length of this arc alpha. See, this is nothing but you would have studied length of a sector. Okay, it's like you have a circle here and you're asked to find the length of, this is the center. Okay, and if you're asked to find the length of this portion, this is a sector, this total is a sector. If you are asked to find the length of this portion, it is enough if you find this angle. If this angle is theta, then the length of this segment is also theta. Okay, so that's the same idea which I have used here. And similarly, in order to find the length of this arc BC, join this point B with the center and join this point C with the center. Find the angle subtended. This angle I am taking it to be some beta, so the length of this arc is also beta. Next, again for this arc AB, you can see that I've joined A with the center O and B with the center O, and this angle subtended, I've taken it to be some gamma, so the length of this arc is also gamma. Okay, so always keep in mind, in spherical triangles the measurement of the angles will be in degrees and minutes. Also the length of the sides will also be in degrees and minutes. Okay, don't search for units of length like meters, centimeters in the questions. You have problems based on this. Now we'll see the derivation of cosine formula. The cosine formula is given by cos A is equal to cos B cos C plus sin B sin C into cos A, where the small letters A, B and C denotes the sides of the spherical triangle, and capital A, capital B and capital C will denote the angles in a spherical triangle. Okay, we have already proved this in the case of a plane triangle in our school, but now we are going to prove the same result in the case of a spherical triangle. And the spherical triangle here under concentration is A, B and C, formed by the arcs AB, BC and CA. Okay, and another point to note is that the center of the sphere will be the center of the great circles. Okay, so this O here is taken to be the center of all great circles, so this is also the center of the sphere. Okay, now keeping in mind, I've taken the sides of this spherical triangle ABC to be marked as such. Guys, how we'll usually mark is that the side which is opposite to angle A will be taken as small a, and the side which is opposite to angle B will be taken as small c, and the side which is opposite to angle C will be taken as small c. That is how we usually mark. I too have marked here like this. And I've already said you in while explaining how to measure the sides of a spherical triangle. If the arc length is given, if the arc length of this AB is C, then which means that if I join this A to the center, and if I join this B to the center, and if I find the angle subtended, that angle will be the same as the arc length AB. Okay, that's what I marked this angle AOB to be small c. Similarly, you can see here, now this arc length BC is taken to be small a. Therefore, I'm joining this B with that center and C with the center, and this angle subtended is same as this arc length small a. Next, for this arc AC, this arc AC length I have taken to be B, therefore the angle formed, angle AOC, I have taken it to be small b. Alright, so this is the basic labeling of this diagram. That's what I've written here. Angle BOC is small a, angle AOB is small c, and angle COB is small b. Alright, now after drawing this, what I'm doing is, you have to keep in mind all the while that all these arcs AC, BC and these AB are all arcs of great circles. That is, you have to imagine, if this is an arc, means that is one great circle which is passing through this. Similarly, if AB is an arc, then there is another great circle which passes through this. If BC is an arc, then there is another great circle which is passing through this. Okay, so just keep in mind there are circles behind the scene. Okay, alright, so now what we are doing is, I'm drawing two tangents. Okay, AE and AD are tangents to the great circle arcs AC and AB. So since, guys, keep in mind, while proving, we are considering only one angle here. Only one angle under consideration is capital A. So I'm just focusing at this vertex, angle A. The vertex which contains this angle A is this. So I'm just focusing this one right now. So what I'm doing here is, we have two circle arcs. This is AC and this is AB. I'm drawing just two tangents to these circles. Okay. So what we are doing is, this is one arc AC, so I am drawing one tangent to it, and this is another arc AB, I am drawing another tangent to it. So this tangent what I am drawing here is meeting this line OB at this point D, and similarly the tangent which I am drawing here, this again is meeting this line OC is extended to meet the tangent at the point D. That's what we have written here. Okay guys, now you can see that actually the angle here is nothing but, this angle A was actually held at up to this time by these two sides. This side B and this side C were holding these two angles. Now you can see that this angle A is held by this straight line AE and this straight line AD. Alright, so the angle DAE is the same as angle A. So the difference is that, so far before drawing these tangents, this angle A was contained by two sides which were sides of a spherical triangle. Now you can see that this same angle A is held by two straight lines, but this triangle, as you can see, is not a spherical triangle, it is a plane triangle. Alright, so that is the idea here. Okay, alright, now actually in this theorem we will have three cases. So first case, you will be considering the sides which contain this angle to be less than 90 degree. Here I have said this side B and the side C is containing this angle A, and I have already said that measurements of the sides are in degrees. Now the assumption which we take here is, both B and C are less than 90 degrees. That's what I've written here. Assume that the sides containing the angle A are each less than pi by 2. That is, your B is also less than pi by 2 and your C is also less than pi by 2. Okay, alright. And further from this figure, what else can we say? So far we had only spherical triangles, but now we have introduced plane triangles also. Okay, so from this figure what we can say, what I've written here, first, angle EOD is the same as angle BOC. What is angle EOD? This is EOD. This is the angle EOD. This is the same as angle BOC. Yes, the angle inside is small a. Similarly, angle AOD is same as angle AOB. AOD. This is the angle which is same as AOD. OB. Yes, same angle is subtended. Small c is inside. Similarly, you can see AOE also. In AOE as well as in AOC. Both are same. The angle subtended is small b. Okay. You just see there's a shifting. So long we had only spherical triangles. Now we are making use of plane triangles. Why are we making use of plane triangles is we already have existing result only in plane triangles. With the help of that, we are going to prove it in the case of spherical triangles also. Alright, that's what we are showing, that these are all equal. Okay, so from the plane triangles here, DEA and DEO. Okay, I've drawn the plane triangles here. I'm going to apply cosine formula. See, in general, how we'll apply cosine formula is if you have a small triangle and I have marked the vertices A, B, and C, and these sides to be small a, small b, and small c. If this is the angle under consideration, means the side opposite to this angle. We'll begin with that. Okay, so a square is given to be b square plus c square minus 2bc into cos of the angle between these two sides. Alright, so that is the normal cosine rule we had. By making use of that, I'm talking for these two triangles DEA as well as DEO. Okay, so first we'll see this triangle DEO. In our question, we have to concentrate only on small a and this capital A under consideration. That's what we are making use of these two triangles. As you can see, the angle subtended is small a, and in this triangle, the angle subtended is capital A. That's what we are making use of these two triangles. So from this, you can see that DE square, see, this is the angle, and the side opposite to this angle is DE. So DE square is equal to OD square plus OE square minus 2 times OD into OE into the angle subtended, that is cos of the angle subtended, cos A. Similarly, in this triangle DEA, you can see that this is the angle we are considering. So the side opposite to that is DE. So DE square is equal to AE square plus AD square minus 2 times AE AD into cos of the angle in between these two sides. The next step what we are going to do is we are going to subtract those two. As you can see, the left hand side was DE square in both the equations. So it will become 0, and this is all ordinary subtraction. I have just subtracted and written here. Alright. Mark this equation as sum star. Moreover, we always know that the angle between a tangent and radius is a right angle. In other words, see, for example, you can see this arc AB. Okay, so this is an arc of a great circle whose center is O, which means this distance OA is a radius. Okay, and this point, at this point A, I'm drawing a tangent. So when I draw the tangent, what will be the angle between the radius and this tangent is 90 degree. So this side is going to be 90 degree. Similarly, this side also is going to be 90 degree. So this angle, I'll mark here. So this angle is going to be some 90 degrees for y'all. Alright, similarly for this arc AC also, as you can see here, I have drawn a tangent here. So which means that this this total angle is going to be 90 degree. Right, so you can see here in triangle OAD, you have one right angle. Similarly, in triangle OAE, you have one right triangle. That is what I have mentioned here. Angle OAD is 90. Similarly, angle OAE is also 90. OAD and your OAE angle is also 90 degree. So when you have 90 degrees itself in this triangle OAD, you have one angle to be 90 degree, and the side opposite to 90 degree is called as the hypotenuse. And now we can apply Pythagoras theorem here. You will have OD square to be equal to OA square plus AD square. Similarly, in triangle OAE also, so this is your 90 degree, and the side opposite to 90 degree is your hypotenuse. So OE square is equal to OA square plus AE square. So that's what I've written here. And what you're going to do is, now we are going to make use of these two equations in the star equation. Alright, so in the star equation we have OD minus OD square minus AD square. So from 3 you can see here OD square minus AD square is nothing but OA square. So substitute in this place OA square. Alright, okay. Similarly, next we have OE square minus AE square. So OE square minus AE square is again OA square. So in this place you are going to substitute OA square. Keep the remaining as such. We'll see what we can do there. Alright. So now adding these two, you will have here 2 OA square minus 2 OD OE cos A plus 2 AD AE cos capital A. Alright. Guys, we are actually nearing our result. We need to find small cos A. So just take that term alone and keep it on the left hand side. Keep the remaining terms as such. Okay. I'm taking minus 2 OD OE cos A to the left hand side, so it becomes plus. And what you're going to do is we just need cos A. We don't need this 2 OD OE and all. So I'm dividing throughout by 2 times OD OE. Alright, so the left hand side becomes just cos A, and when I divide by 2 OD OE, 2 and 2 gets cancelled. You have OA square, right? I'm splitting it as OA into OA. When you divide by OD OE, one of the terms I'm writing it here and the other OE I'm writing it here. Alright, now similarly for the last term also, this 2 and 2 will get cancelled. You are dividing by OD and AE by OE. You are getting this OD OE to the denominator. That's all. Okay, so now what is left to us is we should find the values of this OA by OD, OA by OE, and AD by OD, AE by OE. If we finish that, the theorem is done. Alright, guys, I already said we have two right angles here, OAD and OAE. Okay, so from this right angle you can see that angle A, in this vertex A we had 90 degrees, and in this vertex O we had angle C. You can see for reference here. So the angle here is small c. So I'll just mention that here. Okay, and the angle opposite to 90 degrees is hypotenuse. This is the angle C under consideration. So opposite to this angle C will be named as opposite, and the other side, remaining side, is the adjacent. Okay, so we have two right angles. In these two right triangles only, we are going to use both the sine and cos formula. Normal trigonometric basic functions. Sin theta is given by opposite by hypotenuse, and cos theta is given by adjacent by hypotenuse. We are going to make use of that. So in this triangle we have angle C. So in this C we have to find what is sin C. So sin C is opposite by hypotenuse. It's just nothing but AD by OD. Alright, next you have to find cos for that same angle. So cos C is nothing but adjacent by hypotenuse, OA by AD. So, and similarly you had another right triangle OAE, and you can see that the angle at the vertex O is small b. You can see here the angle at the vertex O is small b for this triangle OAE. Alright, so similarly the angle opposite to 90 degrees hypotenuse, and the side which is opposite to the angle under consideration is the opposite side, and the remaining side is the adjacent. So similarly we have found sin B. So sin B is opposite by hypotenuse, AE by OE, and cos B is adjacent by hypotenuse, OA by OE. That's all. Now we have got to make use of the sixth equation in the last fifth equation. Okay, and as you can see that we have here OA by OD. Where is OA by OD? This one. So this is your cos C. This is your cos C. This will be your cos C. And what is OA by OE? Where is OA by OE? Here. This is OA by OE. This is nothing but cos B. So this is your cos B. Similarly, we have to check where is AD by OD. AD by OD is here. This is your sin C. And the next term AE by OE. AE by OE is here sin B. So you will have here sin C into sin B into your cos capital A. That's how we come in this formula. Cos A is given by cos B cos C plus sin B sin C into cos of capital A. In other words, you can also write this formula as you keep cos A as such. Take this term here. So you'll have cos A minus cos B cos C divided by sin B sin C. You can write it in this way, or in you can just leave it as such.